So now we want to go ahead and look at how would we find the local maximums, the local maxima or minima, um, and therefore the absolute maxima or minima. And the key to all of it is what we call a critical point. So first, let's just define this idea of a critical point, and then we'll talk about why, how it's related to the extrema. So just the definition first. So let C be an interior point in the domain of F. And this just means exactly what it sounds like. It means that it is inside, solidly inside the domain of F. So this just means that it's not one of the endpoints. Okay, so it has to be, if the domain is like 0 to 4, then it's any point between 0 and 4, except for 0 and 4, right? So let's see, be an interior point in the domain of F. We say that C is a critical number of F if F prime of C, the derivative of F at C, equals 0, or, and this is one that's often kind of forgotten, but is equally important, F prime of C is undefined. Okay. So this would mean that C is a critical number of F. And then we call the point C F prime of C, or sorry, just F of C, because we're just looking at the original function, C F of C, a critical point of F. Okay. So critical number and critical point, they're often just used interchangeably because you can move from one to the other rather easily. It just depends on if you're talking about the X value or the point, and it often doesn't matter which one we're talking about. So, I don't know to call this like a theorem, or I guess we can call it a theorem, but it doesn't really have a name or anything. But just the reason that these are important for the extrema is that if F has a local extremum at a point X equals C, then C must be a critical point of F. Okay, so if we have a local extremum at C, then C must be a critical point. So logically, this also means that if C is not a critical point of F, then F does not have a local extremum at X equals C. So we can find an exhaustive list of all of the possible local extremums by finding all of the critical points. Now, it should also be noted that just because there is a critical point at C doesn't necessarily mean that there's a local extrema. So we'll look in a couple of videos about how to definitively say that there is a local extrema. So first, let's just go ahead and just look at how we would find these critical points. And I mean, it's pretty straightforward just from the definition. We just want to find the places where the derivative is 0 or where it's undefined. So we've already done this with a function plenty of times, right? So now we just have to do it with that function's derivative. So we just take the derivative first and then do it with that new function that we have. So if we look at f of x equals x squared, for example, right, then the derivative of f is 2x, right? So we're looking for where is the derivative 0 or undefined. In this case, it's never undefined because the domain is negative infinity to infinity, but it will be 0 at a point, namely at x equals 0, right? So x equals 0 is a critical point of f. So this is where we would suspect that there might be a local maximum or minimum. Okay. Let's look at some more examples. What if we just have something like 1 over x? Okay. So here f prime of x is negative 1 over x squared. And this is not going to be equal to 0 anywhere, right? If we set it equal to 0, we're not going to come up with any x values that will work here. So we're really just looking for where is it undefined. Okay, so it's undefined at x equals 0. Okay, so x equals 0, again, is a critical point. So this is where we would be looking for a local max or min. And this is also an example of where you're not going to find one. Okay. This is going up, basically the limit from both sides is infinity. So there's no really way to talk about a maximum point. Okay, so we'll look at some more examples here. And this is where your algebra skills could really come in handy, because you could end up having to do lots of algebra for these. Okay, so let's say we have something like this equals g of x. Okay, so 1/3 x cubed minus 5 halves x squared plus 4x. So the derivative here is going to be just x squared. So you pull that 3 down and that cancels. Minus 5x plus 4. We want to set this equal to 0. This is a polynomial, so it's not going to be undefined anywhere, so we don't have to worry about that. Okay, so we can factor this as x minus 4, x minus 1 equaling 0. So x equals 4 and x equals 1 are critical points. Okay, these are the places where the derivative is 0. Okay, let's look at h of x equals x squared minus 1 cubed. Okay, so if we want to take the derivative here, we'll go ahead and use the chain rule. Okay, so we get 3 times x squared minus 1 squared times the derivative of the inside, which is 2x. And then we'll set that equal to 0. Okay, so this one's a little bit tricky. Using the zero product rule here, we can look at these as these are like two different factors, right? So this is going to be either 2x equals 0, implying x equals 0, or 3x squared minus 1 squared equals 0. We can divide both sides by 3, which will still give us 0 on the right. Take the square root of both sides, which will still give us 0 on the right. We're going to get x squared equals 1 ultimately. And then we have x equals plus or minus 1. Okay. So 1, -1, and 0 are all critical numbers here. And we don't have to worry about it being undefined, because even though it's written differently, this is still a polynomial. Okay. All right, let's do this one, f of x equals 4x over 1 plus x squared. Okay, so we'll need the quotient rule here. F prime of x then equals 4 times 1 plus x squared minus 4x times 2x over 1 plus x squared squared. Okay, we'll go ahead and simplify the top first. So we get 4 plus 4x squared minus 8x squared over 1 plus x squared squared, which ultimately is going to leave us with negative 4x squared plus 4 over 1 plus x squared squared. Okay. So we want to set this equal to 0. There is a denominator here, so we do want to think about if it's undefined anywhere, but this one's not going to be. Because if you set 1 plus x squared equal to 0, right, if I just do it like over here, you get x squared equals negative 1, and there's no answer for that, right? X squared can't be negative 1. So we don't have to worry about that part. So this is just going to be 0 when the numerator is equal to 0. So this is going to imply negative 4x squared plus 4 equals 0. All right. So we can go ahead and divide by, well, I guess we could just bring the 4 over to the other side and then divide by negative 4. So you get x squared equals 1. So again, x equals plus or minus 1. So our critical numbers are plus and minus 1. Okay, so a few more examples with some special functions. Like if we have sine of x, for example, just to at least put an example with trig in here, even though like I've been saying, we're not going to do a lot of trig. The derivative is cosine, so we're looking for where is cosine of x equal to 0. And this is going to be when x is equal to pi over 2 plus or minus 2 pi, actually just pi k. Right, so you can confirm that with the unit circle. And then we'd say k is an integer. And this is how we write the symbol for integers. More relevant ones to us, maybe something like e to the x. Well, you could probably guess this one from looking at the graph. F prime of x equals e to the x. This is not undefined anywhere. The domain is all real numbers, and it's also not equal to 0 anywhere, right? And you can see that directly if you try to take the natural log of both sides to get the x down from the denominator or from the exponent. You run into the issue that you can't take the natural log of the right side. So this one has no critical points, and therefore it has no local max or local min. Right. Something like the natural log, okay, f prime of x in this case is 1 over x. So x equals 0 will be a critical point because it's undefined at 0. But again, you're not going to get a local minimum out of that because it's going down to negative infinity. All right, what about one more relevant to statistics? The standard normal distribution. So this is the density function of a standard normal distribution. 1 over root 2 pi times e to the negative x squared over 2. So if we find the derivative of this, The 1 over root 2 pi is just a constant, so that'll just come along for the ride. And then we use the chain rule. So this is negative e to the x squared over 2 times the derivative of negative x squared over 2, which will be just negative x, right? Because the 2's will cancel. And we want to set this equal to 0. So now, again, with the zero product rule, we say either negative x equals 0, or the rest of it equals 0. I'll just put, I won't even necessarily write it because we know that can't be 0 because e to anything can't be 0. So there's not even really a reason to look at that. All right, so this is just going to be the x equals 0. And in the probability distribution functions, this is known as the mode. So this tells us that the mode of a standard normal distribution is 0. So last example, let's get a absolute value, or not absolute value, but a piecewise function in there. Okay. The absolute value, actually, since I just said that, is a good example of a place where you do have an absolute or a local minimum at 0, but the derivative doesn't exist there. So another reason why we need to consider the places where the derivative is undefined. So let's look at x squared minus 4x and x squared minus 4. Okay, so this is a pretty short interval that we're looking at here. Might be helpful to graph this one. So we'll just graph them separately, and then we can just kind of imagine where the boundaries are, because we're just going to use this as a reference. We're of course going to rely on the math to actually help us here. So we're looking at the red line between 0 and 1, 1 being right here, closed on both sides, and then the blue line from 1 to 2. So it's basically this little kind of like a V shape, right? Oops, I'm sorry. I just noticed that was cut off. So 0 to 1 for the red line, and then 1 to 2 for the blue line. And so it's like this little V shape in the middle here. So this is a continuous function. As we can see, they're joined at 1, and you could show that with the limit and all that. So we can kind of just see what we should be expecting. We should be expecting to probably have a critical point right here, right at 1. This is 1, -3. And it's hard to really say, but I wouldn't be surprised if the derivative is not continuous right here, or is undefined right there, because it looks like it might be a bit of a sharp corner. So let's go ahead and just differentiate. So we haven't really looked at this, but we can just go ahead and differentiate the pieces. So we'll get 2x minus 4 on this interval, and 2x on this interval. Now really on the transition point, we really can't say that this is true at the transition point. We have to look at the transition point separately. So on this piece, on 0 closed to 1 open, we can say it's 2x minus 4. And from 1 to 2, we can say it's 2x. But at 1, because remember the derivative is really a limit, the left and right hand limits might be different here. So we should consider that point specifically using the definition of the derivative as a limit. So we can use the alternative definition of the limit of the derivative. So if we do the limit as x approaches 1 from the left of f of 1 or rather f of x minus f of 1, because we're using the alternative definition, divided by x minus 1. So on the left side, approaching the limit from the left, we're on this part of the function. So this is going to be the limit as x approaches 1 from the left of 2x minus 4 minus f of 1 in this part is going to be negative 2 over x minus 1. So the limit as x approaches 1 from the left, this is going to be, add 2 to this. This is 2x minus 2, which is 2 times x minus 1 over x minus 1. Okay. So here the x minus 1s will cancel, of course. So we'll just get 2. Okay. So that side worked out pretty nicely. Now we'll do the limit as x approaches 1 from the right side. Whoops, scratch that. That was a mistake, right? I just used f prime. We should have been using f. Okay, so let's back up a second here and relook at this one. So this should have been x squared minus 4x. And then when you put 1 into that, you get minus 1 minus 4. So minus a negative 3. So this is going to be x squared minus 4x plus 3 over x minus 1. So if we just plug this in directly, of course the bottom will be 0. Let's make sure we get 0 on the top. We get 1 minus 4, which will be negative 3 plus 3. So we do. So can we use some algebra, or do we need to use L'Hopital's rule? Looks like we can probably use algebra, because we can do x minus 3x minus 1 to factor the top. All right, so now that cancels. And then the limit as x approaches 1 from the left of x minus 3 would be negative 2. Okay, so we actually almost got the same thing, right? It was just negative 2. So now let's do f of x minus f of 1 over x minus 1 from the right side. So here we're using, it was x squared minus 4, right? Yep. So we get limit as x approaches 1 from the right of x squared minus 4 minus, same thing, really, right? Minus a negative 3 over x minus 1. So this is going to be the limit as x approaches 1 from the right. Negative 4 plus 3 will be a negative 1. Okay. So here we'll definitely get 0 over 0. And then we can easily factor that with the difference of squares formula. Okay, over x minus 1. So we get that the limit is equal to 2. So let me just make sure nothing went wrong here, that we didn't miss a sign somewhere. It doesn't look like it. So this means that this function would not be differentiable at 1 because the left hand and right hand derivatives are different. So again, so I think it's a little, it could go either way looking at the graph, but it does look like it's a pretty sharp transition here, which is typically where derivatives do not exist. So not too surprising here. So anyway, the thing that we want to use this for, of course, is the critical points. So because the derivative is undefined at x equals 1, that tells us that that's a critical point, right? So that's why we needed to go through all of this, right? So x equals 1 is a critical point. And then we need to see if the derivative is equal to 0 at any points on this interval. I don't think that they will, because 2x is equal to 0, x equals 0, which is not in this range, in this interval. And 2x minus 4, that would be equal to 0 at, what is that, x equals 2, and that's not in this range. So it looks like the only critical point of this function is going to be x equals 1, because the derivative does not exist there, meaning it's undefined.